Hi learners, it's Em from Sononerds, and this video is on Unit 12A, Transducer Types. Unit 12A, Transducer Types. As you can see, we've got a 12A, we are going to have a 12B. Unit 12A is going to focus on the characteristics of transducers, how they each create an image, and we'll go over the key definitions to help us understand how transducers do what they do. In Unit 12B, we're going to continue the discussion surrounding resolution. In the third resolution discussion, we're going to explore what elevational resolution is and how the transducer construction affects it. We're also going to touch back on lateral resolution, as now that we have learned more about transducers, there are a few transducer functions that can improve lateral resolution. We're going to start this lecture off then with section 12A.1, definitions. Now the definitions that I'm going to go over here are going to give you more context as we learn about the different transducers and their characteristics. First, we're going to start with field of view. Now, the field of view is the shape that the image takes on. Quite often, it's referred to just as the sector, but there are actually special names given to the shapes that certain transducers create. Sector is one of them, but sector refers to a very specific shape, as a sector is a wedge of a circle, and that is what we're seeing here. So we are seeing a pointy top with a rounded bottom. Kind of looks like a piece of pie, piece of pizza. It is part of a circle. This is the true sector image. We also have something called a blunted sector. The blunted sector is going to have a curved top and a curved bottom. That curved top is due to the type of transducer that we are using. You'll notice that the top of the image matches up with the type of transducer that you're using. We have some transducers that create a very shallow curve on top, and we have some that are going to create a very steep curve on top. We also have a rectangular field of view. This is going to be where the image is flat on all sides with 90-degree angles. And we'll see that the transducers that create rectangular field of views also have some variations. We can get a wide scanning view, which gives a more trapezoid shape to the rectangle. So this is known as wide scan or convex scan. And then we can also see that the rectangle can be steered in different directions, giving it more of a parallelogram shape. In older systems, we saw that the machine did allow us to steer the B-mode scan lines into more of a parallelogram shape. We don't see that as much now, but we do see the parallelogram shape when we are scanning in Doppler mode. We also have some transducers that create flat top sectors or a trapezoid shape. Notice that this one is flat on top but curved on the bottom. This is different than the convex or wide scan that we see with the rectangular variation. That one had a flat bottom. So note that the flat top sector or trapezoid sector does have that curved bottom. And then lastly, we do have transducers that don't create images. Remember, those are dedicated continuous wave transducers. They are going to create Doppler information. So we will see waveforms, but no anatomical image. The footprint of the transducer is the part that comes in contact with the body. Some transducers are going to have very small footprints, and some are going to have larger footprints. The footprint of the transducer is typically the widest the field of view can be at the start of the near field. Depending on the type of transducer, the shape of the footprint is also going to predict the shape of the transducer at the top of the field of view. Footprints of transducers have evolved to match the area being scanned. On the bottom here, we have a small cardiac transducer with a small footprint that is built that way to be able to fit in between the ribs, where general ultrasound transducers are going to use wider footprints because we need more expansive views of the abdomen. Our next term then is crystals. Remember that crystals are the PZT elements, so sometimes we refer to them as ceramic, PZT, elements, crystals, all mean the same thing. But now we are interested in how the crystals are arranged on the transducer face. We can have single element transducers, which is mostly what we've been talking about up until this point, where we have one single element on the face of the transducer creating the sound beam. And as we're going to learn in this unit, we're going to talk more about array transducers, where array transducers are going to have multiple crystals at the face of the transducer. So speaking of arrays, that's our next term. Now arrays, remember, are transducers that have multiple crystals. And we can further define arrays with special terminology regarding the way that those crystals are arranged. So the first one is a 1D array. A 1D array has crystals that are going to be aligned in a singular row. 1D array transducers are capable of creating 2D images, which are just our normal black and white images that we get for most of our exams. 1.5D array transducers are going to introduce crystals that are aligned side by side, but then we're also going to see a vertical alignment as well. Now the 1.5D array transducers usually are going to have a minimum of 3 rows. They can have more rows than that as long as there's not as many crystals vertically as there are across. That is a different type of array. So 1.5D array transducers have usually a larger center row of crystals and then a little bit smaller crystals in rows above or below that center row. The benefit of having extra rows in your transducer face is that now you have more control over how thick the beam is. If we are just using our center row, we are going to have a short elevational thickness, where if we can use more of the crystals in that vertical fashion, we can create a deeper elevational or beam thickness. And the last type of array is a 2D array. Now the 2D arrays are going to have crystals that are aligned more in a square pattern, kind of like a checkerboard. So there are going to be equal amounts of crystals vertically as there are horizontally. 2D transducers are capable of creating 3D imaging. Our next term is going to be channel. A channel is going to consist of 3 things: the crystal or the element at the transducer face, the wire that is connected to the element, and then the machine electronics that are connected to the wire. Remember that those wires are connected to each individual element at the transducer face. This is how we get voltages down to the crystals and how those echoes and voltages return back to the machine during reception. The wires and the machine electronics are going to play a huge role in how we are able to activate the elements to tell them to send out sound, and how we can change some parameters to better listen for echoes coming back. We're going to switch gears on the definitions to look at a little bit more about how focus is created with the transducers. The first idea that I want to introduce to you is the multi-focus, which is fixed in the annular array transducer. Now we're going to get to that a little bit more when we talk about annular arrays, but I want to talk more about how we can have a multi-focus transducer that has fixed focal points. In this type of array transducer, you will see that there are elements that are circular shaped, aligned as concentric rings at the face of the transducer. It looks kind of like a singular element transducer. However, each ring is going to act individually as its own element. By introducing the different rings, we are creating crystals that have different diameters. And if you recall back to our beam anatomy lecture, the size of the diameter is going to directly be related to the depth of the focal point. So when we have larger diameters, we get deeper focal points. And so that's the whole idea behind this multi-focus fixed transducer. Large crystals are going to create the deep focus, as we are seeing in the red. The green crystal is a little bit smaller, so it's going to have a little bit more shallow focus. The blue one, smaller yet, with a shallow focus. And then the orange one is the smallest at the center with the shallowest focus. So these foci are fixed based on the diameter of the crystal creating them, but they all work together to create an image that has multiple focal points going down the field of view. Now the tricky part about this is because we are creating one scan line with multiple pulses, we are going to reduce our temporal resolution, but we are going to have superior lateral resolution throughout the image. So this is a fixed focus because we cannot change that diameter of the transducer crystal, but we still consider it multi-focus because there are multiple levels of foci throughout the image. In this example, when all crystals are activated, the pulse is going to need to be sent 4 times to create one scan line. If we were to reduce the depth and maybe only need it down to where the blue transducer crystal was imaging to, then we would only need 2 pulses per scan line. The multi-focus fixed transducers are mostly obsolete, so we're going to spend a little bit more time learning about electronic focusing, which is how most of our transducers on our modern systems are going to operate. Now, electronic focusing is based on the fact that we have an array transducer, so we have multiple crystals, we have a wire attached to each of those crystals, and we can send a pattern of electrical voltages down to those crystals. So again, electronic focusing is only possible with array transducers. We have to have multiple crystals, each consisting of their own channel, all capable of receiving multiple types of electronic patterns to excite the PZT material in a particular way. When we are using electronic focusing, the machine is capable then of not only multi-focus, but also having adjustable focus. So the biggest part to remember about electronic focusing is how the pattern of the voltages coming down the wires affects the beam. In the first example, we can see that all the voltages are coming down at the same time. All of those elements are going to be activated at the same time. If there is no curve to the pattern, we are going to have an unfocused beam. When we introduce a curve to the pattern, activating our outer crystals sooner than our middle crystals, then we are going to introduce a focus. So when the pattern has a curve to it, the beam will be focused. If we have a very steep curve like we have in the middle, we are going to create a shallow focus. If our curve is a little bit flatter, then we are going to create a deeper focus. So as a sonographer, you have your focus knob on your machine. You can move that around. And as you move that around, that tells the machine, I want my focus set at 3 centimeters. The machine knows exactly what to do, what pattern will achieve a 3 centimeter focus, and it will send that down to the crystals to make that focus. Let's say you add in another focus then. Maybe you have a very shallow focus set. That's going to be created by that steep curve. And then let's say you add in a second focus that's a little bit deeper. That pattern coming down is going to be a little bit flatter curve. So the machine still needs to send 2 pulses because you have 2 foci set, but they are going to have different patterns to achieve the different focal depths. So again, when we have the electrical pattern coming down, activating all crystals at the same time, there's no curve, we are going to get a beam that is unfocused. When we introduce a very steep curve, we're going to activate those outer crystals first. The little wavelets are going to come out, they're going to interfere with one another and create a shallow focus. When we see a flatter curve, those elements are going to be activated first on the outside, but a little bit quicker as we move to the middle, and that is going to create a deep focus. The foci are created by interference, both constructive and destructive, from the little wavelets. Remember those V-shaped wavelets that are coming out of the elements. They're going to work together to create a focused beam, and the machine can dictate where that focus is based on the curved pattern it presents. Moving on to a new concept then, we have beam steering. One of the problems that we encounter with sound is that sound can only travel in a straight line. So as you just saw with the last transducer examples, the beam was heading straight from the ultrasound transducer directly down out of it. And if that was the only thing we could do, imaging in a straight line, all we would get is a very small slice of anatomy directly from our transducer. We wouldn't be able to create our whole image sector. We wouldn't be able to really see much of anything. We'd only get one scan line over and over and over again. So ultrasound system manufacturers needed to figure out a way to move the beam into different directions to get more of a field of view. So now we introduce the idea of beam steering. So to create a full frame, we are going to steer the beam through each scan line that creates a frame. Now there are a few ways that we can achieve beam steering. The first one is manual steering. This is going to apply more to our continuous wave transducer, so we're really not creating an image from this anyway. But the manual steering is us physically moving the transducer into a new position to get a new area of installation. The second way that we can achieve beam steering is mechanical steering. The third is electronic steering, which is also known as phasing, or we can do a combination of mechanical and electronic steering. Mechanical steering is going to require an actual motor within the transducer that is physically going to move the PZT element into a new area to create a new scan line. So we have a motor with the crystal attached, as we can see in this picture here. That motor is going to use electronics and gears to move the PZT crystal, and every time it moves the PZT crystal, a new scan line can be created to complete a full frame of images. Now, the problem with mechanical steering is that these types of transducers, because they have a motor in them, require oil to keep the motor working, very fragile electronics to keep everything working, and it's actually kind of enveloped in this large, fluid, oily, greasy coupling fluid inside the transducer, which actually leaked out quite a bit and would come with kits where you could inject more oil into the transducer. So they worked, and they still work, because we do still use some mechanical steering transducers, but they aren't as practical as our modern day transducers. So to create an image with a mechanical transducer, the element is in one position, a pulse is created, echoes return back to the element in that position, and are processed by the machine. The motor is going to move the element ever so slightly. Again, a pulse is sent, echoes return, motor moves the element again. Pulse is sent, echoes return, and so on, until all of the scan lines are created through mechanical motion by the transducer, and then it will start again at the left side of the image, again sweeping across all the way through the right, creating those scan lines over and over again to create new images. So the big part about mechanical steering is to remember that it does include a motor within the transducer that physically moves the PZT element. Now, while we do still use some mechanical concepts in some of our transducers, the more common and more reliable type of steering is electronic steering, and that is going to be achieved through something called phasing. So electronic steering is how most of our modern ultrasound systems create our sound beams, and similar to how we talked about with electrical focusing, we needed to have a curve in the pattern of voltages coming down. To steer the beam, we now introduce a slope. So if you have a curve, the beam is focused. If you have a slope to your pattern, then you're going to have a steered beam. Now, the reason that we call this phasing is because there is a delay in the time that those crystals are being activated. Different slopes are going to have different delays or different phases, and that is going to create a different amount of steering in one direction or the other. So to determine how a beam is being steered, all we need to do is connect the first pulse to the last pulse, so a straight line through there, and then we are going to draw a perpendicular line directly from that line. Remember that sound travels in a straight line, so if we draw a straight line from that imaginary line that we use to connect the first and last pulse, we are going to see that this type of slope creates a steer to the left. Compare that to this one over here, again connecting our first and last pulse, straight perpendicular line from it, we are going to see that this type of slope creates a steer to the right. So when you have a sloped pattern, you are steering the beam. We can kind of prove that then with our no slope. If we were to connect left to right here and then draw a line straight from it, we will see that this pattern creates a straight beam, no type of steering. In transducers that only use phasing to steer the beam, all of the elements are needed to create the sound beam. So all of the elements are activated. The pattern in which they receive the voltage is going to determine the steer of the sound beam. I do have a little star next to that because we are going to learn later that there are linear sequencing transducers that only use phasing for some of the crystals. So I do want to highlight again, if you have a beam that solely relies on phasing for its steering, it is going to use all of the crystals. If you have a transducer that does not rely on phasing for steering, then it's going to use phasing in a little bit of a different way, and we'll cover that later. But for the most part, a phased transducer is going to use all elements to steer the beam. So again, we have all of our pulses coming down, hitting the crystals at the exact same time, sending that pulse out, and we are getting an unsteered beam. It is coming directly from the face of the transducer, from that kind of front line of the pulses. Compare that to then when we have a slope introduced, those voltages are coming down at an angle. We're activating our rightmost element first, kind of working our way across the face of the transducer, still activating all the elements. But because of the way those wavelets are going to interact with one another, what we end up getting is a steered beam to the left. So when the rightmost element is activated first, we are going to see a beam steered to the left because of interference, constructive and destructive. Compare that then to the beam that faces the other direction. If our leftmost crystal is activated first, again, we have a slope, so we are going to have a steer. Those wavelets again are going to interact with one another, causing the beam to steer to the right. So the biggest thing that you need to look for is there a slope? If there is, we're going to have a steer. Connect your first and last pulses, draw a line straight out from that connection, and that's going to give you the direction that the beam is steered. A steeper slope is going to cause more of an angulation of steer, or a flatter slope is going to cause the beam to not be nearly as steered away from center as it would be with a steep slope. Now I mentioned that we can also combine the mechanical steering and the electronic steering. Now the combined steering is not found in very many transducers. In fact, it's mostly just found in our 2D array transducers, which create 3D ultrasounds. So what we will see is that big square matrix. Remember that 2D array looked like a checkerboard? That's going to be connected to a motor. And that motor is going to move the entire checkerboard. And so what it's going to do is move it, most likely in either the elevational or lateral plane, and then we're going to get scan lines created from all three planes. The up and down axial, lateral side to side, and elevational, which is more like front to back. By moving that large matrix through the area, that is how we are going to get all the slices in all the directions to be able to make 3D images. So combined steering is typically found in dedicated 3D transducers. Now, before we leave the concept of electronic focusing and electronic steering, I do want to point out that really for the most part, we're combining the electronic phasing to produce both focused and steered beams. So if the pattern coming down the wires is sloped and curved, we're going to see a beam that is both steered and focused. In our first example here, we have a very flat pattern of electrical voltages coming down the wires. They are going to interact with the elements all at the same time. There is no slope, there is no curve, so we are going to see no steer and an unfocused beam. Notice on our next example over here though, we have a curve, so we're going to see a focused beam, and we also have a slope. Our voltage timing for the outside elements are different, so we see a slope. So again, we've recognized that there's a curve, means there's going to be a focus. There's a difference in timing between the outer edges, which means there's a slope. So we can connect the first down to the second, draw an imaginary line directly from that connection, and we're going to see that this curve is going to create a focused, left steered beam. Compare that to the other side then. Again, we have a curve in place, so we know it's going to be focused. Outermost to outermost, there's a difference in timing. So connect the two, draw a line straight out from it, and you're going to see that this is a focused, steered beam to the right. And this is how most transducers are going to operate. There's going to be some sort of curve to the pattern and some sort of slope to the pattern to create beams that are both focused and steered throughout the image. So now we know that there are beams that are going to use all the elements, induce those phased delays to create focused steered beams. So remember, that is the pattern of the electrical pulse is going to determine which direction that beam goes and where the focus is on it. Now there are other transducers that only send out ultrasound waves based on sequencing. Now sequencing is going to use small elemental groups to create a beam, and it's going to do so across the surface of the transducer to create the whole field of view. So in our example here, we can see that groups of elements are being activated and they are sending a beam straight from the transducer face, because sound can only travel in a straight line, but it's going to travel across the surface of the transducer, create the whole image, start again, create the whole image, start again, create the whole image over and over again as the frame is refreshed. So again, to compare and contrast sequencing versus phasing, sequencing is going to use small groups of crystals to create a beam. Those are not going to be steered typically. They're going to leave straight from the transducer surface. Phasing is going to require all of the elements working together using electrical patterns to steer the beam in particular directions. Some of our more modern sequencing transducers are also going to use some phasing within these small groups of crystals. We'll talk about those a little bit more when we get to those types of transducers. Another concept that I want you to be familiar with is the idea of a damaged PZT crystal. So when a crystal becomes damaged, it's possible that it will affect the image. Depending on the type of transducer, the image can either completely disappear. If you only have one crystal and it gets damaged, it makes sense that the whole image would be gone. You might just have dropout in one very specific area, or you might see some reduced function, some reduced image quality because of broken PZT crystals. On the types of transducers that will display a very specific area in relation to the damaged PZT crystal, what you're going to see is kind of a dark fuzzy line emanating from the transducer surface in your image. So the best way to check for this is to activate the transducer, no gel on it, and just take a look at that first little bit of sound that you can see in your image. So we've got quite a few examples here. So this is the transducer face up here. This is where the PZT crystals would be represented. And what we're seeing here is this dark line traveling directly from where those PZT crystals are. This line indicates that there is a broken PZT crystal here. It's either not sending sound out or it's incapable of receiving echoes. So something is wrong with this channel. Could be the PZT crystal itself, it could be the wire. Same idea with this one. This is a curvilinear transducer. We are seeing a gap here within those horizontal lines. That means, again, there's a broken PZT crystal or a broken wire. Same thing here. We are seeing a dark line traveling from the very tippy top of the transducer image. It's important to note that when there is a damaged PZT crystal, this dark line, again, comes from the very, very top of the image. It is not shadowing being created by a structure within the image. It is going to emanate directly from the top of the picture, and that is the best way to recognize if there are broken PZT crystals. These are going to be more prominent in our sequencing transducers because remember, those only use really small groups of crystals. So if one of that small group is broken, it's more likely going to show up in our image. Compare that then to the transducers that use all of their elements to create a sound beam. When you have one broken crystal out of all of those elements, you're probably not going to see a whole lot of change in your image. However, if more of those elements become damaged, there definitely will be an effect on the image, typically resulting in either poor steering or poor focusing. The most common way that crystals become damaged on a transducer is typically by dropping the transducer. So you need to be very careful with your transducers, take care of them, make sure you don't bang them around or drop them on the floor. And then the other way that the channel can become damaged is by rolling your machine over your cord. Remember, all those wires connecting to the crystals have to travel through the cord and back to the machine electronics. So your cord, if you have 250 elements, you have 250 wires running through that cord. If you run over it often enough, there's a chance you might damage a few of those wires. If those wires get damaged, then the voltage information and the echo information cannot travel between PZT and machine, and we might see dropout in our image because of that as well. The last term that I want to introduce to you then is 3D and 4D imaging. When we are using our grayscale imaging, our B mode, we are talking about 2D pictures. And 2D pictures are made out of pixels, which is short for picture elements. So all those little dots on the screen are pixels that line up with the information that the machine has gathered and has turned a pixel on or off to make gray, black, white, whatever. Those are 2D pictures. When we use 3D imaging, we are gathering information from all three planes. So we have our axial, lateral, and elevational planes. And when an image is created using all three planes, we are making pictures now out of voxels. And voxels are volume elements and are the building block of our 3D pictures. 3D imaging is best when trying to determine a volume of something. Because it is taking measurements in three different planes, we can calculate volumes of fluid like in the bladder or in cysts or heart chambers, gallbladder, that kind of stuff. However, most people think of 3D imaging as being the cute baby pictures that we see. While it is a very fun and heartwarming experience for parents to see their unborn children in 3D imaging, basically what the machine is doing is just calculating the volume of the baby, and then it does this thing called rendering, where it kind of interprets all of that information and then puts an overlay over it to make it look like soft tissue. So this is where we kind of get the cute, fun pictures that we see. But 3D imaging truly is a volume type of imaging and is still kind of finding its way in the diagnostic world. Again, as of right now, it's mostly for entertainment in the fetal OBGYN practice, but we are finding more and more uses to use 3D imaging for diagnostic pictures. Now, you may also have heard the term 4D imaging. All 4D imaging is doing is adding in the element of real time to 3D. A static 3D image is still a 3D image. We are seeing the volume being represented within the image. If we were to watch the machine capture the 3D image, render it, and show it moving in real time, the 4D, the fourth dimension, is that time piece of it. So we're watching it in real time. 3D imaging requires a lot of processing. To do it in real time for 4D requires even more processing. So we see that the frame rate ends up being really poor with 4D imaging. Therefore, we see a very degraded temporal resolution, but the technology is getting better and faster, and we are able to now watch like heart valves open and close in 4D. So there are more uses for 3D and 4D imaging other than the entertainment factor, but they are still relatively limited. And we'll go over a little bit more about this when we get to the 3D transducer section. So speaking of the 3D transducer section, it is at the end of our next section, which is 12A.2, transducers. So in this section, we are going to go over several types of transducers. I believe there are 9 of them that we are going to cover. There are 6 transducers that you really need to focus on. That's going to be your mechanical transducer, the annular transducer, linear, phased, convex, and vector transducers. We are going to talk about some other types of transducers just so you can kind of understand the whole picture. So we're going to start with the more simple transducers, working our way towards a little bit more complex transducers. I do want to highlight that, again, some of these transducers are obsolete, but we are kind of learning the evolution of ultrasound and how we've been building on the ultrasound technology to create the modern transducers that we have today. As we go through each transducer, I am going to go through some very key things on these transducers. So these are the things you are going to want to know. You are going to want to know what image shape the transducer creates, the crystal shape and the number if it's significant. A lot of our transducers just have multiple elements. That's kind of mostly what you need to know. There are a few that only have one or very particular shapes of them. So focus on those when we get to those ones. You'll also want to know what happens when a PZT crystal is damaged, how the beam is steered, is electronic or mechanical, how focusing is achieved, is it mechanical, fixed, electronic, where we commonly use these types of transducers, what applications. And I'll also go over how the image is created. Now, you don't necessarily need to know step by step how the image is created, but you should have a rough idea of how the crystals are activated, how the transducer is creating every single scan line, how a full frame is created. You should be able to kind of understand those concepts. Throughout the years of teaching this, learners have found that it is the most helpful to create a chart of all of the transducers and their characteristics. Again, you should really focus on the mechanical, annular, phased, linear, convex, and vector transducers. as those are the most common transducers that you will be tested on. The other ones kind of build off of those types of transducers. And then if there are any terms that we go over in the second half, we've covered most of the concepts in the definition section. So make sure to refer back to section 12A.1 if you can't remember what electronic focusing is, or if you need a refresher on what it means to have mechanical steering. So the first transducer is called a Pedof transducer. Now this is also known as a blind Doppler transducer. These are continuous wave transducers dedicated to making continuous wave ultrasound. So these type of transducers do not create images. On the front of the transducer, there are going to be two crystals. They usually take on a semicircle shape. If either of those two crystals become damaged, then the transducer is no longer going to work because it either can no longer transmit a signal or it can no longer receive a signal. This is one of the only transducers that requires manual steering. So as a sonographer, you are physically moving the beam around trying to get the area that you want. The focus is going to be fixed either as an external or internal. We commonly use these in the vascular application, vascular in this case also including the flow within the heart, looking at flow of the valves. So the blind Doppler transducer, or the Pedof transducer, is going to have two crystals at the front of it. One is continuously transmitting, the other one is continuously receiving. And where those two lines overlap is where the ultrasound information is coming from. So transmission beam, listening area, this is where we are going to get our ultrasound information from. These types of transducers can be connected to our ultrasound machine, and when we use it with the ultrasound machine, we would get an image similar to this, where we would be able to recognize the Doppler signal being produced by the blood vessels that are moving through that overlap area. There are other machines that assess vascular physiological flow, and we use very similar transducers, but they don't create an image necessarily like this, where they would create more of an outline of an image showing if a waveform was biphasic, monophasic, that kind of stuff. And we're going to cover a little bit more of that when we get into our Doppler section. So the biggest thing with Pedof transducers, they are continuous wave transducers. They do not create an image, and they are manually steered by the sonographer, listening for different sounds, looking for different waveforms that are being created to recognize where they are at within the anatomy. The next type of transducer, this is an important one, is the mechanical sector transducer. Now the mechanical transducer is going to create a sector shape. So remember that has the pointy top with the curved bottom. The crystal found within the mechanical transducer is circular, kind of coin shaped, and there is only one of them. So if that one PZT crystal becomes damaged, we are going to completely lose the image. That one crystal is attached to a motor. So because this is a mechanical sector transducer, the steering is mechanical on this. So there is a motor that is going to physically move that coin-shaped crystal into different directions to make a full field of view. Focus on the mechanical transducer is fixed. So that means that it is either going to have a lens in front of the transducer, or it's going to use a curved single element, which is that internal focusing. So external or internal, but it's going to be fixed focusing. Our mechanical sector transducers were originally used for cardiac applications, and that is because they had a small footprint and the way that the sector image interacts with the body. So the nice part is that the transducer sits right here. You can fit it right in between a couple ribs. The sound is going to be very narrow at the top field, so it can make it through the rib space and then start to widen in the far field where the heart would be sitting. So we get very narrow near field because we don't need this information. This is all going to be shadowing an artifact from ribs, and we widen where we're very interested in the actual heart or other anatomy that we're looking for. This is an example of what the mechanical transducer looks like. Inside the casing here, there is a motor. There's electronics for the motor, and up at the scan head here is where we are going to see that circle coin attached to a motor. The electronics then are going to move the motor around. This whole dome type area is also filled with like that greasy, oily coupling gel in here as well, because we don't want air in there. And that was part of the problem. These types of transducers either leaked that coupling oil out, and that caused problems, or air would get in here and cause problems as well. So the mechanical transducer ended up being an excellent introduction. It did what it needed to do, but there were a lot of problems with the actual transducer itself. So the mechanical transducer, in the most strictest of sense, is obsolete at this point because of those problems that we were having. It helps us understand how we once used a motor to move the crystal to get those different sound beams to create a sector. So remember, the pulse is sent from the crystal, echoes come back, it moves a little bit, pulses are sent, and it's going to sweep across the whole anatomy, creating our sector field of view. Now, some of the good things about our mechanical transducer, it had that small footprint so it could fit in between the rib space as well. And because it only used one PZT crystal, if that PZT crystal was relatively small, we got a pretty good focal point for our lateral resolution, but it also was pretty narrow in the elevational resolution. The next type of transducer is the mechanical annular array transducer. Now, it's mechanical because it has a motor in it, and it's an array because there's multiple elements. So the mechanical array transducer also is going to create a sector-shaped image. The crystals on the annular array are going to be concentric circles. So you're going to have a large diameter crystal, smaller, 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 getting to the center one. There are multiple elements creating those concentric circles. So because there are multiple elements, that's why it's an array transducer. They all move together as one circular coin shape. Now, the way that the annular array transducer creates the image is that each of those circles is responsible for part of the image. The most center circle is responsible for the near field, where the most outer circle is responsible for the far field. So if one of those circles were to become damaged, what we would see is horizontal dropout. And that is because of how the machine uses those crystals to create the image. So in this example down here, the tip top here is made by the center smallest crystal. The next part down is the next outer ring, outer ring, outer ring, with the far field being created by the most outer ring. So when we get a damaged crystal, we are going to see side to side dropout because of how each crystal is responsible for a layer of the image. Now, all those crystals are going to, again, be working kind of as one unit. They are, again, attached to a motor, and that motor is going to move all of those concentric circles to a new area to achieve a new scan line. Now, the focus on the annular array transducer is technically fixed, but we achieve it electronically. Each of those crystals is going to receive one pulse, and each of those crystals has its own focus. So the really awesome part about the annular array transducers is that it has amazing lateral focus, because each of those crystals down the image is going to have its own focal point, but the temporal resolution really suffered because we needed to send out 4, 5, 15 pulses for one scan line. Surprisingly though, this was still used mostly as a cardiac transducer, again because of its small footprint, fitting in between the rib spaces and the type of image that it created. So in our example here, again, we have this annular transducer. The motor and all the electronics are within the housing here, and then up at the scan head is where we would find those concentric circles attached to the motor so it can move around. Again, same idea as the mechanical. There's a bunch of fluid, oily grease in here working as the coupling method. So this one still had the same problems of air getting in there, oil leaking out, but we now have a little bit more variable in depth, and we have better lateral resolution because of all those individual elements. So again, the annular array transducer is basically obsolete at this point, but it shows us how we have now moved to an array transducer, still using the mechanical part of it, but are advancing in our understanding of lateral resolution, elevational resolution, and how to create the entire field of view. So similar to the mechanical transducer, we have the circular elements all moving as a group together by motor. For each crystal that is being activated, they are going to send their own pulse out with their own focus. So in this example, if we have 4 crystals activated, 4 pulses are needed for each scan line. And you can see in this picture up here as well, when the orange ones come out, they are only responsible for the first part. The green crystal would be responsible for the next part down in the image, blue for the next furthest part, and then red being responsible for the outermost part of the image. So the largest diameter crystal is responsible for the farthest field, and that goes back to our understanding of how crystal diameters work with focal depth and divergence. On this bottom picture here, we have a very, very, very old ultrasound machine. It has an annular transducer connected to it here. So again, we can see the casing of the transducer. This is the motor head up here, going to have all that fluid oil coupling material up in the front here. And we can see the picture that is being created here is a sector picture. We've got the pointy top with the wide bottom. And again, remember, our smallest, most central crystal is responsible for the near field. Our largest, most outer crystal is responsible for the far field. If that central crystal were to break, we would lose our near field image. If that outer crystal were to break, we would no longer have side-to-side view in that far field. And then again, any other crystal in between would cause dropout going in between side to side in our image. The next transducer that we're going to look at then is the linear switched array transducer. So the switched refers to the fact that the crystals are either on or off, and then array tells us that there are going to be multiple crystals on this transducer face. The image shape that the linear switched array transducer makes is rectangular, and the crystal shape is also rectangular as well. They are lined up along the transducer face. When they started, it was more around like 30 to 64 crystals. As they became a little bit more involved, we're getting closer to like the 200 range. And because of the way that the switched array transducer works, it's going to use very small groups of crystals. So if one of those crystals became damaged, it became very obvious in our image by vertical dropout. We kind of looked at the ultrasound images before where we could see that black line coming from the very top of the picture. It is the linear transducers that tend to show that type of dropout. So vertical dropout if one of those crystals becomes damaged. This type of transducer did not have any steering because it is using sequencing to create the image. The focus on these types of transducers used fixed focusing. These are kind of first iterations of transducers, so we haven't figured out the electronic piece of it yet. So we have fixed focusing using either an external lens or curved elements. And then we commonly use these types of transducers for vascular and maybe some general work as well. We have a picture here of a linear switched array transducer. So notice how big the footprint is of this really old transducer. There's crystals lined up along the transducer face, and it's going to use sequencing to create its image. So it's going to use very small groups of crystals to send sound directly from the transducer face into the body. So because of this wide footprint, that means that the top of our picture is very wide as well. And that is why it needed to be so big, so we could get more of a view of the abdomen or more view of the vasculature. Something like this would not work for rib spaces. We would have tons of rib shadowing, really obscuring a lot of the information that we would be looking for if we were trying to look at the heart. So this type of transducer in its original form as the linear switch transducer is obsolete now, but we actually do use linear transducers on our modern machines that use sequencing, but also introduce some phasing into it as well. That's why it's important that we learn about this first type of transducer so we understand how our modern transducers have evolved. So the linear switched array transducer used sequencing to create the image. So again, it would activate small groups of crystals. Those small groups of crystals would send out their tiny little wavelets. Those wavelets would interact together and typically just send a beam straight down into the anatomy. So this really old picture here, you can see how those scan lines are made, sending that sound information straight down into the body, and then the echoes come back to create the scan line. So there may have been like 3 crystals that made this scan line, another 3 crystals that made this one, 3 that made this one, and so on and so forth. Each group being activated, moving across the transducer face to create all of these scan lines, thus creating a full rectangular image. Now this image in particular is very, very old. We know that because we are having actually some gaps in here, so we're losing a lot of our spatial resolution. Notice there are no focal points in here. It is just automatically focused either by the lens that is built into the transducer or having curved elements that are creating these scan lines. And this one actually happens to be of a fetal head. This is the outside of the head, this is the falx, and this looks like maybe the choroid plexus up in the brain. So the linear switched array transducer, again, small crystals activated to make a straight beam, to make that straight scan line directly from the face of the transducer. Now at this point, a lot of people wonder, well, why can't we just use one crystal, one scan line? Wouldn't that help with the resolution that we're seeing here? And the answer is actually no, because remember, when we activate one small sound source, we create those tiny little V wavelets. And those V wavelets are going to diverge very, very quickly. So we want that interference, that constructive and destructive interference, to make the shape of the beam stronger and in the direction that we want it to go into. So one tiny little sound source on its own is going to diverge. We're not going to get very much as far as meaningful echoes from that. But when they work together, we can receive echoes and process them into images. So the Pedof probe is very much still used. The blind Doppler transducer continuous wave still very much used today in those vascular and cardiac applications. The mechanical transducer, annular transducer, and the linear switched transducer are all mostly obsolete at this point. So we're going to switch over into transducers that we commonly find on our modern systems. Now the first one that we're going to take a look at is the phased array transducer. The phased array transducer is going to create a sector-shaped image. The crystals on the front of the transducer are rectangular shaped. And remember, as far as these numbers go, you don't have to memorize exactly how many are on there. I would maybe look at the pattern that the phased array transducers tend to have a little bit less than the rest of our transducers. But the phased array transducers still have quite a few crystals at the front of the transducer, usually averaging somewhere between 64 and 128. Now looking at the title of this transducer, it's a phased array. That should immediately key us into the fact that this type of transducer is dedicated to phased steering, phased focusing. So because of that, all of the crystals are going to be used to create our image. So if one of those crystals become damaged, one of the 64, one of the 128, we're not going to see an immediate effect on our image. It's after quite a few of those crystals become damaged that we might start to see some poor steering or poor focusing occur. So to highlight that again, damaged PZT crystal on a transducer that uses all of their crystals is not going to create an obvious dropout in the image. I already kind of alluded to this, but steering and focus are both electronic. Remember, we're using curved electrical patterns to make a focus, sloped electrical patterns to make the beam steered. These types of transducers then are commonly used in the cardiac setting, again because of the small footprint and the shape of the image. So the phased array transducer gets its name because of the way that it creates its beam. Remember, it's going to use all of the crystals, and it's going to activate those crystals in a very specific pattern to not only focus, but to steer the beam. Now, my graphic that I made here is not the best, but I think it gets the idea across that as we introduce those different patterns, we are going to see different amounts of steering with downward slopes to the right, steering to the left, and downward slopes to the left, steering to the right. And the closer that those voltages arrive together at the same time, we are going to see less and less steering to the point where it would be emitting directly from the transducer straight down. So again, all crystals are used to create the beam. The pattern of the voltages is going to focus or steer the beam. Slopes mean steered, curves mean focus. Here's an example of an image using a sector transducer. They're most commonly used in the cardiac setting because we can fit the transducer face in between the rib spaces, and the way that the near field of the sector is very narrow compared to the far field. If we had information from either side here, all it would be is probably most likely lung or rib shadow, so we're just not interested in that information. So the shape of the sector is very conducive to also seeing in between the rib spaces. Because this is an electronically steered and focused transducer as well, it has the capability of adjustable focus, so we can move this little caret wherever we want, That's again going to change the pattern of voltages to make a focused beam wherever we have decided as a sonographer that we want it to be. We also can add in multi-focus, but remember, anytime you add in another focus, we are adding in extra pulses. Extra pulses mean reduced temporal resolution. When we add in those extra focuses, we can improve our lateral resolution, but the phase transducers are going to use a lens to have a fixed elevational resolution. The next transducer is the Linear Sequential Array Transducer. Now these are our modern transducers, remember, so they don't work quite the same way as the linear switched array transducer worked, but they still use sequential scanning. They also are capable of using some phased technology as well. So the images created by the Linear Sequential Array Transducer are rectangular. The crystals are also rectangular, and there are quite a few of them across the face of the transducer. Just like our sequential linear, if one of those crystals were to become damaged, we would notice a vertical dropout in our image. And the steering that is used for the linear sequential array is typically going to be no steering for our normal B mode, but it can use some electronic steering for other applications that are used with this transducer. And I'll show you that in a minute here. The focus on these are also electronic, and we commonly use these types of transducers for vascular and small part work. So here we have a couple different types of linear sequential array transducers. They often come in multiple types of frequencies. In fact, all of our transducers come in multiple frequencies. It depends on what you're using them for. If you have a very deep barrel-chested male that you really need to get kind of far in to the chest with a phased array transducer, you're going to choose a low frequency phased array transducer. Compare that to a child, you're going to use higher frequency phased array transducer. Same idea with the linear sequential arrays. Depending on what you're trying to image, you're going to choose a transducer that matches best with the depth and anatomy that you're trying to image. So this linear transducer here has a bandwidth of 14 to 5 megahertz. This type of transducer is best for small parts, for our breast, testicle, thyroids, that kind of stuff. The 8.3 has a bandwidth of 8 megahertz down to 3 megahertz. This one is going to be best used then for more vascular applications, looking at carotids, looking at the vessels in the arms or in the legs. This little guy here is called the hockey stick, and it has a super high frequency. It goes all the way up to 18 megahertz. So this type of transducer is really, really awesome for superficial skin structures. We can also use this for some very small vascular structures. Use this quite often for dialysis mapping. Use this quite often in pediatrics because their vessels are so tiny that we want to see them well. So we have options within all of our transducers as far as frequencies go. And then I also want to point out that each of these has a different size footprint. This one is very small, this one's kind of in the middle, and this one tends to be the largest footprint. So here are some examples again too of using these transducers, that larger footprint. Remember, however big this is, because this is a linear sequential array transducer, however big your footprint is the widest that you're going to be able to see in this near field. So everything visible under the transducer is going to match up. So if this is 5 centimeter footprint, the top of our picture is also showing 5 centimeters of anatomy. So this picture here is of a testicle. We have the right and the left one here, so right and left. And again, it's using sequencing to create the B mode pictures. So it's activating a small little group of crystals over here to get this scan line. Then it activates the next group of crystals to get the next scan line, and so on. And it's going to move all the way across, creating all those little scan lines from those small groups of crystals all the way across, starts over to refresh the image, sequencing across the transducer face. Same idea with this transducer. It has a little bit smaller of a footprint. This might be more along the range of like 4 centimeters, 3 centimeters. That's what we are then going to see anatomy-wise below it. So the transducer footprint on our linear sequential array transducers matches up exactly with the width of the picture that we are seeing. Notice too that these have focal points or focal zones. The linear sequential array transducers are going to use that phasing technique, introducing curves to the patterns that activate those small crystal groups to create a focus. And that's why we say that these linear sequential array transducers do use some phasing techniques to create the focus and to create some other image shapes. But for the most part, when we are using the linear sequential array transducer to create a black and white picture or our B mode pictures, we are using sequencing. Again, small groups of crystals are activated to send a beam directly into the tissue directly from the transducer face, travels in a straight line. So if these are all horizontal, we're going to see a perpendicular sound beam coming out from them in a straight line. However, we can introduce some phasing when we want to activate a machine's capability of providing a wide scan, or what we call a convex scan. So notice now that we have these kind of little wings on the outside of the image. Normally we have just a straight down rectangular on the sides. In this case, the sonographer has activated the option for wide scan or convex scan, and now we're getting a little bit of phasing on those outside crystals. The phasing is steering the beam off to the side, and then as we get back through the middle, we're using sequencing again, and then some more phasing to steer off to the side again. So rectangular images can be converted into wide scan or convex scan images by phasing or steering the crystals on the outside to make the picture a little bit wider. Again, the widest that this can be on top though is the footprint of the transducer. We're just increasing the field of view a little bit more further into the image by using that wide scan or convex scan. Relatively modern, but on the older side of machines, used to let us steer the B mode. So here's an example of steering that is being used to direct all of the scan lines to the right. So this type of transducer, again, is the linear sequential, but it's using some phasing to create a parallelogram shaped B mode. We don't see this quite often anymore. It's not as necessary now that we've gotten better at actually being able to steer our color box. So the color box you can see in this image here, but I want to bring your focus more down to this picture here. This color box is using scan lines that are being steered using phasing. So the most common place that we will see that parallelogram, that phasing steer of the rectangle is when we use color Doppler or pulse Doppler. We are going to use phasing to steer those small groups of crystals, the sound beams that they create. We're going to use that phasing to steer it off to the side. So the crystals that are making the B mode picture are still using sequencing behind. So all the black and white are sequenced crystals going across the transducer face, making the black and white image. The crystals then that are being used to make the color Doppler and the pulsed Doppler are going to undergo phasing. So those patterns, those sloped patterns, and those small groups of crystals are going to undergo that phased sloped pattern to create the steered beam that we see in the color portion. So with linear sequential array transducers, remember that B mode is typically achieved through sequencing unsteered small groups of crystals. If we steer at any point, we need to introduce phasing, and that is achieved electronically through the patterns of voltages applied to the crystals. The second part that I want you to remember is that phased transducers activate all of the elements. When we introduce phasing into our linear transducers, we're still only phasing small groups of elements. We are not phasing all of the crystals at this point, just those small portions. Now the next transducer we're going to talk about is the curved linear sequential array transducer. So we just talked about linear sequential array. Now we've got the curved linear sequential array. And the curved linear sequential array basically works the same exact way as the linear. The only difference is how those crystals are arranged on the transducer surface. So what we end up seeing with the curved linear is a blunted sector. We're going to see the same rectangular shaped crystals at the front, 200 to 300 of them. They still produce a vertical dropout if they become damaged. We still have either no steering or electronic steering, like we talked about with that phasing. Focus is still achieved by electronic. And because of the very, very wide footprint and because of the wide field of view, These are most commonly used for abdominal, vascular, and OBGYN work. So I've got a couple examples of transducers down here on the bottom. This is probably the one that most people associate with ultrasound. This is our curvilinear transducer. If we were to look at the surface of the transducer here, we would see all of those tiny little rectangular crystals aligned, matching up with the curve of the transducer face. We also have other types of curvatures that are a little bit more steep, and these are going to be called microconvex transducers. And that's because they have a very small footprint and a really tight curve. And these types of transducers are going to prove very useful in certain applications. So again, we have the blunted sector. Notice that the curve of the transducer follows the curve of the top of our image view. So we see a blunted sector still with the curve on the bottom. And we see again too that the PZT damage is going to result in a vertical dropout from top to bottom of the image. The curvilinear sequential array, or which is also known as the convex transducer, is really our modern transducer that we use for so many applications. Convex means to bow outward, and that's exactly what the surface of the transducer is doing. The crystals then are arranged along the transducer surface as a 1D array side by side. So very similar to the linear sequential, it's going to activate small groups of crystals. The sound beam is going to travel directly away from the transducer surface, but because we are working with a curved surface, we will see sound waves kind of being displaced off to the side, a little less straight down, and then again being directed off to the side because they are being emitted directly from the curvature of the face of the transducer. And that's what we are seeing in these pictures here. So this is that kind of wider, softer curve that we are seeing here that we commonly use for OBGYN and abdominal work. We are seeing that the small group of crystals here is emitting a straight sound beam from the curve to create kind of this wider angle. The small group of crystals that are being activated here are going to send their sound beam directly straight down. Again, directly from the transducer surface means that as they follow the curve, we're going to see a widening on the edges. So that is why the curvilinear transducers are awesome. We get a very wide field of view. Now these two pictures on the bottom here show us those microconvex transducers. Microconvex transducers are capable of fitting into smaller areas, but then still providing that very wide field of view. So in theory, the microconvex transducers could be used for cardiac applications if we wanted to, but it would still end up interfering with a lot of rib shadow in this kind of near field, which is not really what we want. So that is why we stick to the sector phase arrays for cardiac. In this image though, we are looking at a fetal head. The transducer is placed in the anterior fontanelle, which is a soft spot on the skull on newborns, and we can image through that fontanelle to see the fetal brain. So we are seeing all the way through the brain, some midline structures, the sulci and the gyri, getting down to the posterior part of the head. That microconvex, very, very small footprint, but gives us an amazingly wide view beyond that footprint. This example over here, notice again how the curve is following the transducer curve. This is from a transvaginal transducer. This image is actually from an ultrasound phantom, which means that a company built a fake body to mimic what we would see in a real body. But I liked this picture because it nicely showed that curvature of where those crystals are emanating from. So the very small footprint of the transvaginal transducer can fit within the vagina, but then still gives us a really nice wide view of the pelvic anatomy because of the way the curvilinear sequential array transducers emit sound beams. Again, we can have multifocusing and adjustable focus with this type of transducer. Is going to use those curved patterns when activating those small groups. We can also activate a wide scan on these as well. I would just end up steering those outer groups to make the field of view a little bit wider than what is natural for the transducer. But really the biggest benefit of this is that it is going to follow the curvature of the transducer to create that super wide field of view. Our next transducer is called a vector array transducer. And this type of transducer is going to create what we call a flat top sector or a trapezoid sector. So we can see that down in the bottom here, we've got a flat top to our image and rounded bottom. Now this is probably looking very similar to the wide scan that we saw with the linear sequentials, and it is, except for this curved bottom part. We're still going to see that curve with the vector transducer. Crystal shape is going to be rectangular with about 200 or so on the surface of the transducer. Now the vector array transducer operates kind of in between a phased array and a linear sequential. And when a crystal is damaged, we're going to see more of a reaction as if it was phased. We're going to see poor steering and focusing if enough of those crystals become damaged. Steering is performed electronically using phase delays to change the direction of the sound beam, and focus is also achieved electronically using curved patterns to create a focus. Now the vector array transducers come in a bunch of different styles. We have some that have very, very small footprints like the one you're seeing here. Those are going to be more likely used for cardiac. They also have some that are very wide footprints, and we are going to use those more for abdominal, vascular, or even OB/GYN work. Now what's interesting about the vector array transducer is that it does combine the phasing from the phased array, but the small group activation from the linear sequential. So we see different patterns activating groups of transducers, but the intent of that is to steer them. So we can see from this top picture here, we have a relatively small footprint, but we are getting a pretty wide view in the far field, and that is because we are using a little bit larger groups of crystals to steer this way. Another large group of crystals to steer this way, and continuing that phasing to steer in different directions. So vector array transducers do not use all of the crystals to create the image. They use a little bit larger groups with phased steering to create the wide field of view. As I had mentioned, the vector array transducers do come in a variety of styles. Some of them are going to have smaller footprints, which typically have that 1D array, fewer crystals along the front. And some of our vector transducers we will see will have quite a bit wider or taller footprints. And that's because it's not uncommon for vector transducers to come in the 1.5D array format. However, it's important to mention that any of the transducers that we've talked about can come in the 1.5D array format. However, we've been talking about most of them in the 1D array arrangement. And anytime that a transducer uses 1.5D arrangement, then the elevational resolution of that transducer will be improved. So again, the vector transducers really do kind of combine the phasing of smaller groups of elements to create steered sound beams to create the full image. The last type of transducer that we're going to discuss then is the 3D transducer. Now, I don't have this set up in the same way as the other transducers because there's a lot of variety in how the 3D transducers work. But the biggest thing that you need to know about 3D transducers is that they are made up of 2D arrays. Remember, our 2D arrays are our checkerboard type setup, meaning that there are the same number of elements horizontally as there are vertically along the transducer face. The 2D array in a dedicated 3D transducer then is typically connected to a motor, and that motor is going to sweep in one direction while the transducer gets information in the other directions, and because of that, it simultaneously gets information from all three planes. It's then going to take the information from all three of those planes to render an image. Render basically means to make sense of everything, so again, it's going to take that information from all three planes, kind of put it together to make that 3D image. There are quite a few ways that a 3D transducer can be made. The one up on top here, this is a linear 3D transducer. We have a curvilinear 3D transducer, and then we have a microconvex 3D transducer that is used in transvaginal application. All of these are going to have that 2D array setup. They're going to have what looks like a checkerboard of elements at the front of the transducer. Most of our modern 3D transducers have anywhere from 2,000 to 9,000 elements at the face. Again, those elements are capable of getting information in all three planes all at one time. And if we were to be watching a 3D picture live, what we would consider to be in real time, that is the fourth dimension or 4D image. Now, a lot of people think that you have to have a special transducer to create 3D images. But in reality, the 3D image is created by the machine. It's the rendering piece of it that the machine does to make sense of all that planar information that it got. So if you have a 1D transducer, but have a machine capable of 3D, you can actually manually sweep through using your normal transducer, and the machine will still do all the 3D calculations. The benefit of having a dedicated 3D transducer, again, is that motor that's inside physically moving your 2D array, and the pictures are just much more crisp, much cleaner, and are typically going to be more diagnostic than a manually swept 3D image. So I've got a few examples of 3D pictures and a 4D picture as well here, and the different applications that we can use them in. On the top here is a transvaginal ultrasound, and what we commonly use 3D imaging for is to look at IUD placement. So this picture here is a longitudinal image of the uterus. This brighter white spot here is the IUD within the endometrium. We are using a 3D transvaginal ultrasound here. So this is a convex sequential linear transducer. The image was swept in both side to side, front to back, up and down, and then the machine takes those 3 planes to render our 3D image. And here what we are seeing is a coronal view of the uterus. This is the endometrium here, and we can see the IUD is placed centrally within that endometrium. So this is a very common way that we like to evaluate the placement of IUDs. On the bottom here is a 4D image. And again, that's because we are watching this occur in real time. The machine is constantly gathering information in all 3 planes, rendering it very quickly, providing the overlay, and then displaying what it has found. So here we are looking at an aortic valve. We can see the 3 leaflets. We can see it opening and shutting. We can see some of the other soft tissue support structures that are around it as well. But we are really focusing on how the valves open. The 3D part of it gives us a sense of depth to the picture, a sense of volume, and really just a sense of real-life imaging. This picture shows us how the machine can kind of, again, make sense of all 3 of those planes. When you sweep through your anatomy, quite often you'll see all 3 planes. So here we have a lateral picture, side to side. This is our axial picture, up and down. And then this is our depth picture, kind of front to back. And it takes all 3 of those planes, remember X, Y, Z, takes all 3 of them, figures out where they intersect, calculates the volume, and then our ultrasound machines now kind of provide like the soft tissue overlay, so it looks a little bit more like real tissue. So here we can see what appears to probably be about a 12-week fetus in 3D. We can see the uterine wall, we can see the cord attached to the uterine wall, we have a little foot and a leg, genitals here, arm and a hand up by the head. So it makes sense why a lot of parents enjoy getting the 3D fetal ultrasounds, because it makes it feel very real. It's easier to see. It feels like you're actually looking at a baby instead of kind of this black and white skeletal appearing structure. As far as 3D imaging goes and diagnostic value, in the fetal setting, we don't really have much for it. We might use it to take a look at the lips. We might use it to take a look at the spine. But beyond that, 2D imaging is really going to be more diagnostic. In the cardiac setting, again, we can look at the valves moving in real time, which is actually pretty neat. You can see how well they're closing and opening and how the leaflets are activating together and coming together in just a different view than you can get in 2D. But again, we're still really limited on the diagnostic value of 3D imaging in most of our ultrasound applications. And that brings us to the end of our transducer types lecture. Now remember, there is a second section of Unit 12 in which we are going to talk more about that elevational resolution, which I have mentioned a little bit throughout this lecture. We're going to take a closer look as to what that means now that we know what transducers are and what they're doing. But for this part of the lecture, I want you to, again, to focus on those 6 transducers: mechanical, annular, phased, linear, convex, and vector. Know the information that is involved in those charts and know how the images are created. In general, if we look at the phased, the linear sequential, and the vector transducers, the phased transducer uses all of its elements, uses electronical patterns to steer and focus the beam. The linear sequential transducers use sequencing to create the full field of view. They use electronic focusing and are capable of phasing if wider views are needed or if we turn on color or pulse wave Doppler. The vector transducer is going to be a combination of the two. The vector transducer is going to electronically steer and focus its beams, but instead of using all of the elements, it's going to use groups of elements like the sequential. So the vector phases like a phase transducer, but only a group of elements like the linear sequential. The mechanical and annular transducers kind of show us where we've come from and discuss a very important lead-in to how we now steer and use array transducers. You should be aware of how both of those types of transducers create images, why we are at a disadvantage using them, and then really go through all those definitions, make sure you understand how to determine if a beam is focused, how to determine how and if a beam is steered, and be able to generally define most of those terms. Now in your workbook you have a bunch of activities that you can go through practicing those concepts that we learned about in this unit, and then of course you have your nerd check questions, which are the open-ended questions that you can use to make flashcards and test your knowledge on this material.